Hello people, welcome back once again. My name is still Richard. It has not changed. So we are still working on the quantum mechanical model of the atom, and this is the last part of it. Today we are going to tackle electron configuration. So when we talk about electron configuration, what we are trying to say is how are the electrons represented. Basically, what is the address of the electron? That is electron configuration. And if you could remember from our last chapter, we discussed the quantum numbers. And we stated that quantum numbers are basically like the address of the electron. So how the address are written is the electron configuration. Now, there are three scientists that work into how these address should be written. But before that, a little refresher on quantum numbers. When we discussed quantum numbers, we said there are four quantum numbers. The principal quantum number, which is represents the shell or the main energy level of the atom or where the electron resides. And then we did azimuthal quantum number, which also represents the subshells. And we did the magnetic quantum number, which also represents the orbitals that the electrons reside in. And last but not the least, the spin quantum number, which is if either the electron is spinning up or is spinning down. So an electron configuration is how we write these quantum numbers. Now, if you have something like this, I know some of you are already familiar with electron configuration. If we have electron configuration and somewhere in there we have like say 2px2 over here like this. Now, this is what we call spectroscopic notation, and this represents the exact address, or in quantum sense, the chance of finding an electron, right? So over here, these two would represent the principal quantum number, which is n. So principal quantum number. This p, or in this is also the shell, right? This p would represent the subshells. So we go subshells, and this x here would represent the orbital. So in the principal quantum number we have the subshells, so the principal quantum number is the shells. Inside it we have the subshells. Inside some subshells, it's not all subshells, inside some subshells we have orbitals. So this x would represent orbitals. And this 2 here is just the number of electrons in the orbital, right? In the orbital. That is this 2 here. So now that you know, this is what we call a spectroscopic notation, right? Or presentation. So that is how you represent the electron configuration. Now, as I said earlier, there were 3 scientists that did whose work stayed and then made the rules to how we write these address. The first one is what we call Aufbau. So the Aufbau of Aufbau principle. Now let's take the Aufbau principle. So Aufbau said that when filling the shells or the subshells of an atom, electrons tends to fill the ones with lower energy first before going to shells or subshells with higher energy. Now, why is this true? This is true because of law of conservation of energy. The electron wants to conserve energy, or the atom wants to conserve energy and be stable. So by so doing, it is not going to jump over filling a lower energy orbital or a subshell first before going to a higher energy. You are climbing stairs, right? Assuming you are climbing stairs. You don't just jump, right, to the 10th stairs and then jump to the end of the stairs. Same way applies to electrons when you are filling them. You start the first step, the second step, the third step. You build momentum gradually as you go on. So that is Albert principle. The Albert principle states that electrons fill orbitals. Now, this could be subshells, this could be shells, but it fills orbitals with lower energy first before filling orbitals of higher energy. Now, you might say, how do you know that an orbital has a lower energy or higher energy than some orbitals, right? How we do know that is by two ways. The first way is, just thinking about it commonsensically, and the next way is thinking about it mathematically. The first way is if I have an atom, right? Let's say this is the nucleus of my atom, and over here are the shells, right? If I have my atom like this, and I'm trying to fill it, the electrons which are negatively charged, right, that are getting attracted by the nucleus would fill the spot that is closest to the nucleus first. Because of gravitational forces or electrostatic forces of attraction that exists between the positive and the negative charge, it will be here first. So the positive charge could hold it in place. If you put the electron here, or the electron just go onto the other shell, now the distance between them is very long. And just as gravitational forces, electrostatic forces also depends immensely on the distance between the particles. So the longer the distance, the weaker the force. And the weaker the force, the harder it is for the atom to hold, or for the nucleus to hold this electron in place. So it will bring it closer to it so that the distance is cut short and the energy is increased, or the force is increased, and it can use that to hold it in place. That is a commonsensical way of thinking about the shell. But how would you know? If you have like let's say a shell with let's say the 4S shell or 3D shell, or let's say 2P shell, how would you know? Because these cannot be drawn as this, right? Or like you don't really see these drawn out as this. Now on the MCAT, what is the fastest way to figure out which or one of these has the highest energy? Now there's a simple mathematical approach that you could keep in mind. So the simple mathematical approach is just basically N plus L. Now, when we were doing the quantum numbers, we said N represents the principal quantum number, right? And L represents the azimuthal quantum number, the azimuthal or the angular momentum quantum number, right? And just now, when I was doing the spectroscopic notation, right, I said that the principal quantum number, when I wrote this, I said this, the 2 was the principal quantum number. This also is the subshell, and it represents the azimuthal quantum number, and this represents the shell. This represents the orbital. So to figure out which one of these has the highest energy so that you fill it up with electrons first, it's just basically adding the principal quantum number to the angular momentum or the azimuthal quantum number. How do you find the azimuthal quantum number? Because in almost at all instances, the principal quantum number is given. Just that the angular momentum or the azimuthal or quantum number L is represented with a number like S, D, P. So how would you know? When we was doing the quantum numbers also, I said that the shells, right, or the principal quantum number goes in the form of SPDF, right? I said SPDF. And I was like, oh, when I was a kid, I used to watch this Power Rangers cartoon. It was called SPD Space Patrol Delta or Super Patrol Delta, something like that. And when they transform, they go SPD emergency. So that is how, I keep this in my head. So you go SPD emergency, and then I'm just representing this by like a fire. Fire is an emergency, like an emergency. So let's get back to it. This S right here is the zeros represented by 0. This P right here is represented by 1. This represented by 2. This represented by 3. Why are these represented by such numbers? Now, when we was doing the quantum numbers, we said that the principal quantum number is denoted by n. And then the azimuthal quantum number is basically all integers from 0 to n minus 1. Right? So that is how we found the azimuthal quantum number. So let's say you have a principal quantum number of, say, 3. What will be the azimuthal quantum number? Now, one thing you need to put in mind that the azimuth, unless the principal quantum number is 1, unless it is 1, the azimuthal quantum number is always a set of numbers. Because if it is 1, then it will be like 1 minus 1, then it will be 0. So from 0 to 0 is just 0, right? But if it is any number aside 1, the azimuthal quantum number is always a set of numbers. So over here, we assume our principal quantum numbers to be 3. It being 3 means that our azimuthal quantum number would be 0 to n minus 3. And what would that be? 0 to n minus 3 is 2. So from 0 to 2 is a set of numbers. So you go 0, 1, 2 over here like this. Now assuming our azimuthal, our principal quantum number was 4, this will be 0 to 4, and then therefore it will be 0, 1, 2, 3, 0, 1, 2, 3, right? That is how it would be. These, right, the azimuthal quantum numbers, these numbers represents the subshells, right? And the 0, 1 represents the S subshell. So the 0 is the S subshell as I put over here. The P is the 1 represents the P subshell, the 2 represents the D subshell, and then the F represents the 3 represents the F subshell, right? Now if you dig down into the magnetic quantum number, the magnetic quantum number is also found by the integers, both negative and positive integers of L. So from the negative integer of L to the positive integer of L. The negative integer of L to the positive integer of L. So that would be negative L to L. And let's say we came here, right? And then our L was, let's say, 0 to 2. Our L was 0 to 2. We picked the number that it is 2. Like the last number that over here we found that it is 2. So let's say it is 2. It's going to be, so 2 will be like negative 2 to positive 2. Right? Negative L to positive L. And in so doing, it's going to be negative 2, negative 1. Now 0 is part of it. 1, positive 1, and then 2. This would represent, this right here, would represent the orbitals, right? So if you do the math correctly, you found how many numbers here? 1, 2, 3, 4, 5. 5. And what we said the azimuthal quantum number that we got here was 2. So if you come here, you know the azimuthal quantum number 2 represents the d azimuthal quantum number. Therefore, the d subshell has 1, 2, 3, 4, 5 orbitals. That's basically what it is. That's basically what it is. So let's boil this up and then come over here. As we were saying, how do we know that an orbital has a higher energy than the other? Now you could just, the SPDF is arranged in increasing order of energies. So S has lower than P, like as the number goes up, the energy also increases. So if we want to find any of these, which one has the highest energy, like for instance, the 4S, all we have to do is the 4, right, is the principal quantum number 4 plus the azimuthal quantum number L, which in this case S is 0. So then you get 4. So 4, and then you are comparing it to something like 3D, right? For the 3D, let's bring it over here. The 3 is the principal quantum number, so it's going to be 3 plus D. Now D is the azimuthal quantum number 2 over here. So 3 plus 2, which will give you 5. So by so doing, when you realize that 3D has a higher energy than 4S, even though 3 is bigger, is smaller than 4, the 3D orbital has a higher energy than 4S. So those are some of the things that you need to think about, and the nuance that you also need to put in mind when you are filling an electron. So that is the Albach principle, right? Now, with the Albach principle, because most of filling the electrons really comes from the Albach principle, the next two principles are, just laws and statements. They cannot really be twisted and that, but they are straightforward. The ones that have some connotations and nuances to it is the Albach principle. So let me get rid of this one real quick and let's do something over here real fast. So now, using the Albach principle, we can arrange a series, or we can arrange the electrons or the orbitals in increasing number of energy, right, and trace how it increases. So first of all, let's start with 1s. 1s. We come here 2s, 3s, 4s, 5s, 6s, and then 7s. These are the s orbitals. Let's say we have the principal quantum number up to 7. They can go on and on. If the atom is getting bigger, or if they discover bigger atoms or elements, the principal quantum number goes on. So now let's talk about the p orbital too, because it goes from sp. The p orbital would pay attention here and see where you start numbering the p orbital. The p orbital will start from the second principal quantum number, because technically, if you use the Albach principle, like the math that I did over here, and if the principal quantum number is 1, you cannot have a p orbital, because it will be, the azimuthal quantum number will be 1 minus 1, which will give you 0. Now, there isn't any positive to negative integers of 0. It's just 0. So it's just 1 orbital, and that is the s orbital. So technically, you cannot find p orbital with the first quantum number. So, but if our quantum number is 2, then we can find the p orbital, because it will be what? 2 minus 1, right? So the azimuthal quantum number will be n minus 1, 0 to n minus 1, which would be what? 2 minus 1, which will give us 1, right? So if we have this one, now we have negative and positive integers of 1. So it's going to be negative 1, 0, 1. And how many are these? It's 3. 1, 2, 3. So which orbital, which subshell has 3 orbital? P orbital. Or which subshell is represented by 1? P orbital. So when your energy increases to quantum number 2, you get a p orbital. So you don't start with 1p, you start with 2p. Now where do you start with 2p? Here, 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 here. What I suggest is, since the energy leaps, right, from one orbital to the other, you don't start over here because the 1s has already been filled. And then the 2s would be filled. You're going to start from here. In between the 2s and then the 3s over here is going to be your 2p. Now once you get that, follow the same trend. 2p, 3p, 4p, 5p, 6, 5p, 6p, and then 7p. So the 7p is between the 7s and then the 8s, right? Same thing goes if you're trying to fill the d orbital. The d orbital can technically exist on the n equals to 2 quantum number. It has to exist on n equals to 3 quantum number due to the same reason why the p orbital can exist in n equals to 1 quantum number. So for that matter, you start also from here, right? You go 3d, 4d, 5d, 6d, 7d. I'll end it over here. And then let's go to the f orbital, right? Same thing, it goes that way. You start over here, 4f, 5f, or you could go 6f, but I'll end it here. So once that you have arranged it like this, now what you have done is you have arranged the electron configuration to the 7, the n is equal to 7 principal quantum number in increasing order of energy. So if you want to know how it is filled up, let me use blue. We will first go here, we'll first start filling the s1s orbital zoom, right? And then we'll fill the 2s orbital zoom, right? So let me make it a little bit aesthetically pleasing to the eye. Like that. Goes like that. It will come over here. It goes over here. Right? Then it goes. So when it comes here, the trick is that, so when it goes like that, you come over here, it will be down here, zoom, then it goes up like this again. Right? So when it comes up like this again, we go this way, then we go that way, then we go this way, then we go that way. See how it goes? Makes it simple, makes it beautiful, right? So then you can show the arrows that we went this way, up, down, up, down, up. How beautiful it is, right? But one thing is that trying to do this on the MCAT, right, is dangerous because you really have to know the nuance, the calculation. If you do know it, beautiful, go with it. But if you really want to know the nuance, if you do not know the nuance and then the exceptions to rules, and you try to use this, you might end up messing it up, right? Even me, I'm not 100% completely sure that what I have done here is perfect. So somebody like me who is not 100% sure that I could go off of this, how would that represent my atom or my electronic configuration? The periodic table, right? I'm going to clean over here. Okay. The periodic table is one way to realize or to also read the electronic configuration. And in fact, it is the simplest way to go about it. Now, let me give a freehand sketch of the periodic table. I'm not a good artist, so don't. Okay, so this is my periodic table, right? Freehand sketch periodic table, right? Across the period and the group. Our next topic, by the way, or our next chapter, by the way, is periodic chemistry. So we're going to go there. So when you take the periodic table like this over here, when we was doing the quantum numbers, we discussed this. If you go and watch that video, all this block, right? All this place over here, right? It's called the S block. Those that live on the S block. The S block because, let me write S, P, D, F over here. S block because for you to be technically, right, the valence electron is in the S orbital, the S block or the S orbital. The valence electron is the outermost electron of the atom. And they are basically the, so the S block is basically the alkali and then the alkali F metals. Alkali F metals. So hydrogen plus all the highly reactive metals, hydrogen, lithium, beryllium, sodium, magnesium, all of them have their valence electrons in the S block. And over here, I fit this over here. This is not the transitional element. This is the lanthanides and the actinides. You know, when you really see the periodic table, they usually separate this and put it under here. Not because it is anything special, but because they just want the periodic table to look good. It's for aesthetics, aesthetically pleasing. But really, the lanthanides and the actinides goes over here. So let's say the lanthanides, then actinides. They go over here, right? And those are the F block dudes. Them brothers that live on the F block. The F block. Now the F block, because their valence electron falls in the F orbital. Right? And over here, your transitional metals, the beautiful transition metals that gives brightly colored solutions, they go over here. All of them is over here, right? And we call all of them the d orbital. All of it is the d orbitals right here. And we have our last but not the least, by here, the last, the p orbitals. So the S block is the alkali F metals. The F block is the lanthanides. I'll just say lan/actinides, right? And the D block is block, not orbitals, but it's fine. The D block is our transition element or our transitional metals. Transitional metals because they have multiple oxidative states. That is why they have different colors, because different oxidative states absorb different wavelengths of light and hence gives different colors. So the D is the transitional metals, right? And the P is your anywhere from your halogens to your noble gases, and your semi-metals that falls in here are all p orbitals. So halogens, chalcogens or chalcogens, and your noble gases over here that don't react to anything, they all fall in the p block or the p orbital. Their valence electrons falls over there. So if you have this visual representation of the periodic table in your head, because you will be provided periodic table on the MCAT, in your head, when you are told to write an electronic configuration or a question about electronic configuration, just pull the periodic table out. You will see this is S block, F block, D block, p block, right? And I numbered 1, 2, 3, 4, 5, 6, 7. They are the quantum numbers. So this is the first quantum number, second quantum number, third, fourth, fifth, sixth, and then the seventh. So on and so forth. So that is how you do it. Now, how do we really represent the electronic configuration using the above principle? That basically or generally how we represent electronic configuration. So if you are representing an electronic configuration, let's say anywhere except hydrogen and helium, where their electronic configuration is just 1s1 and then 1s2, respectively. English is not my first language, guys. Respectively, right? All other electronic configuration, you can take the noble gas, right? So it wasn't just hydrogen or helium. So hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, right? So all the way up to fluorine, you have to write. You don't really have to write all of them up because you could use helium to represent this group too. So pardon my mistake. Except hydrogen and helium, the rest you can shortcut it by taking the halogen it comes closest to. Let's say we are representing the electronic configuration of our atom, fluorine, right? Fluorine is the 9th atom. Right? So fluorine is our 9th atom. If you are representing it, we will pick helium. We put helium here, so fluorine, like that. Fluorine. Miss fluoride is Miss fluorine. We pick helium. Right now, what has helium taken from the electronic configuration? It has taken 1s, 1 and then 1s2. It has taken both of them. So the next one that would come here is we're gonna start here, right? So we go like the 2s. The 2s will take what? 2 electrons, and then we go to over here is the p orbital, right? 3p, so 3p6. You know how I took my time doing it? I know some of you would are very versed in it, could just do it off, but slow down. Catch yourself. Do not move faster than yourself. Then you are prone to make more mistakes. And the MCAT just, backs you on that because they know that, oh, you think this is trivial. So you're just gonna push your way through. Take your time and do the thing. I did this. It didn't take much time. 20 seconds. I thought about it. I'm done, right? So that is how you represent fluorine, and it goes for any of the elements that you would take. Take it, you write it, basically like that. Okay. Now that is the end of the Albert principle. So after Albert principle, clean. We go to the Hans rule of maximum multiplicity. Hans rule of maximum multiplicity. I don't know, for the English speakers, the word multiplicity might mean you probably know the meaning. It's mundane to you, but for some of us non-English speakers, when we hear a word like that, maximum multiplicity, we are like, oh, is it the maximum amount of multiplications you could do? Well, that is the first thing that comes to my mind. But well, let's go into the thing. So the Hans rule of maximum multiplicity states that electrons would prefer to fill empty orbitals first before pairing up. They would prefer to fill empty orbitals first. So with a subshell that has a degenerate orbitals, electrons would fill empty orbitals first before moving to fill or before pairing up. So let's write it here. Given a subshell, right? Given a subshell with degenerate orbitals. Now, one thing that I need you to put in mind, with degenerate orbitals of the same energy level or the same principal quantum number energy level, comma, the electrons will fill empty orbitals first before pairing up. Right? Because an orbital can take two number of electrons. So this rule would apply to only orbitals or only subshells with degenerate orbitals, right? That is the only orbitals they would apply to, or the only subshells they would apply to. So it would apply to the P subshell, it would apply to the D subshell, it would apply to the F subshell. It wouldn't apply to the S subshell because it doesn't have any degenerate orbital. So if we take the P, right? We take the P orbital, for instance, we have Px. Let me represent it like this. If we take the P orbital, we have Px, Py, and then Pz, Pz. Where I'm from in Ghana, there is a town or a city center called PZ. PZ. It says that the electrons would fill the empty ones first before pairing up. So let's say you have 12, let's say you have like 7 electrons or 8 electrons left to fill in an atom, right? What they will do is that they will first fill up like this. 1, 2, 3. They fill up like this. Empty seats first before they start to pair up. Before they start to pair up like that, like that. Now you get to know why the spin is up and down, right? And not up or down in the same orbital. So this is how it will feel. Same thing applies to the D orbital. So for the D orbital, you have D1, D2, D3, D4, and then D5. Same thing, you would wanna fill them separately first. So you go 1, 2, 3, 4, 5. Before you pair them 1, 2, 3, 4, 5. Like that. Now, where is this applicable? Like, if you are doing the electron configuration, where is this applicable? It is applicable in elements, like any element that have a degenerate orbital, so that you do not go fill it all up first, like fill these two and just leave this, and it doesn't get some. Atoms will always prefer stability over energy consumption. If it is stable for them to exist in like just a parallel or just partially fill, if it's more stable for them to exist in that way, they will spend energy to exist in that way. They will not choose energy over stability. So that is just the Hans rule of maximum multiplicity. Nothing too deep, nothing too wide. Then after that, after the Hans rule, 1, 2, 3, we go to the Pauli's. Pauli. The Pauli's exclusion principle. Now the Pauli's exclusion principle, depending on which book you read or how you Google it, comes in 2 forms, right? But I haven't really seen anything or any book out there. Maybe my research is shallow. I haven't seen any book out there that is combining like both, or saying that there is one police exclusion principle and then the other one. But let's do both just in case. So the first one states that no two electrons can have the same set of quantum numbers. Right? It's basically cut across not only in atomic physics or quantum mechanical chemistry. It also comes in biology too. No two organisms would ever be like identically, both structurally, genetically, whatever, identical. They will not be the same, right? There will always be a tweak. Same thing applies to the electrons. The electrons, no two electrons can have the same set of quantum numbers. In other sense, no two electrons can have the same set of address. Maybe you live in the same address with your mom, so you both have the same address. But in this case of electron, it doesn't exist like that. They have one has its own, the other one has its own. That is the first Pauli's exclusion principle, or the first one. And the second one is that no orbital have the same spin. Right? No orbital has the same spin in them. So that is why it is always spin up or spin down, because the spin needs to be counterclockwise. They need to be opposite to each other to keep them revolving. Right? So that is the first one. The first one is no two electrons could be identical, have the same set of quantum numbers. And the second one is also saying that no orbital can have the same electrons, or two electrons with the same spin. If we have two electrons with the same spin, then the first one would be wrong, because then we can have two electrons with the same set of quantum numbers. But if we comes and say that we cannot have the same spin in one orbital, then it means it has to be different, because the spin number has to be different. So that is the Pauli's exclusion principle. Now we're done with it. Let's move on to the exceptions, like how the exceptions, not really an exception, but basically rules and common sense ways. If we are filling cations, positive charge particles, or anions, that's how it's spelled. Anions. See? Well, you get it. So cations, positively charged species, right, means that they lose electrons. They lost electrons. Now, how do we write the electronic configuration of a species that is losing an electron? That is where you have to incorporate your thinking about energy conservation and stability. That is when it has to come to mind. When an atom is rather gaining or losing an electron to become ionized, right? That is where your energy conservation and electron or an atom stability comes in place. And as I told you earlier, stability, atoms really love to be stable than spend energy as compared to spending energy, right? So if an atom is losing electrons, how is it done, right? The first rule is that take the electrons, right, from the orbital or the subshell, the orbital, with the biggest or the largest quantum number. The quantum number first, before you move on to any other one. So if you are an atom and you are losing an electron, first of all, you take it from the biggest quantum number first, before you go to the subsidiary, the lesser quantum numbers. So you could use like an example, if we have like an electronic configuration of Let's take iron, Fe, ferrous. So writing the ground state electron configuration of iron would be something like this. 1s2, 2s2, 2px, 2py, 2pz, and then we go over here to 3s, 2px2, 3s2, 3p, x2, 3p, y2, 3p, z2. Then we go to 4s, 4s2, and we go to almighty the d, 3, d1, 3, d2, back over here, 3, d3, 3, d4, and then 3, d5. So writing the ground state electron configuration for iron would be, all of these is one subshell but with separate orbitals. Same applies to over here with one subshell but separate orbitals. Same applies over here. So we start filling it from 1s. 1s we get 2. 2s we get 2. Now if we get to 2p orbital, since it has a degenerate orbital, we fill each individually first. 1, 2, 3. Before we come back to fill it. Like that. Now we said that a degenerate orbitals, right? Once you have a degenerate orbitals with the same energy level. So with the same energy level, now 2px is of a different energy level than 3p because this is the second quantum number. This is the third quantum number. So they should be the same for the Hans rule of maximum multiplicity to apply over here. So from here we go to our 3s. We fill our 3s. Same thing applies to the 3p. So the 3px get 1, 3py get 1, 3pz get 1 before we come around to fill it up like this. We go to 4s. Now you would say that 3d, right? The number is smaller than 4s. So why don't we go fill 3d first before we come to 4s? But once again, we did the energy calculation to figure out that which orbital has the highest energy, and it was n plus L. So this 4s is going to be 4 plus 0, which will give us 4. But this 3d here is going to be 4 plus, what did we say that d was? It was SPD, F, and this was 1, 2, 3. 0, the S was 0, P was 1, D was 2, and then F was 3. So it's going to be 4 plus the D, which is 2, right? And it's going to give us 6. Oh, this is 3. So, sorry, let me give you 3, which is going to give us 5. So 5 has this orbital, has higher energy than 4s. So in that case, we will start filling 4s first. So we fill the 4s. Then when we come to 3d, same rule that applied to the p orbitals, it goes 1, 2, 3, 4, 5. Right, but it needs 6 electrons. So then we start coming back to pair it up like that. Now, if you did not follow the rules, you would have done something like this: 1, 2, and then these 2 will not be filled, which is wrong. Follow the rules. Take your time. Breathe. Okay, so this is how that goes. Now, for ground state ion to lose 3 electrons. Let's say we want to achieve ion 3, right? What are we going to do? So first of all, we take the electrons from the atom with what? The highest principal quantum number first. That is why I say take the electrons from the orbitals with the biggest quantum number first. So when we look over here, the orbital with the biggest quantum number is the 4s orbital. Pay attention that when we was filling it, we did fill the 4s orbital first before we fill the 3d orbital. So technically speaking, we should take the electron from the ones that we fill last, because like what? Last in, first out. But this is not how it works. This goes by the biggest quantum number. So it will be the 4s. So we're going to take 1 electron from the 4s orbital to get ion plus 1. We take another electron from the 4s orbital. Now the 4s orbital gone. Right? We've taken 2 electrons. The next electron comes from the one still with the highest principal quantum number, and that will be the 3d. Now, you would say that, how would you do this too? So sometimes you will land on something like this, and it has electrons to the orbitals has degenerate orbital. Where do we take the electrons from? In that case, you take it from the one that has the highest azimuthal quantum number, as I said. Now the one that has the highest azimuthal quantum number, so we take from this one. So the ion 3 plus electronic configuration will be something like 1s2, 2s2, 2p6, 3s2, 3p6, no 4s. You go to 3d, 5, because 1, 2, 3, 4, 5 electrons left in the d orbital. So that is how you go about cations. Now for anions, negatively charged particles, you are gaining electrons. You are gaining electrons to become negative charge. So in that case, what happens, the rules that you follow the regular rules. The regular fundamental rules of what? The regular fundamental rules of filling electronic configuration. The same rules goes, Alport's principle, Pauli's, whatever, Hans rule. That is the same thing you're going to follow for negatively charged anions. There isn't anything fancy over there. So that is one thing right there. By the way, I'm not a teacher in class. I'm just a student. I'm prepping for the MCAT just as you are in the first video that I made. I just seen it fun, and it's more that I learn it more when I teach. So this is my way of learning. Dimagnetism and then paramagnetism. Now, dimagnetism and paramagnetism comes from electronic configuration and how the atom loses or gain electrons. It's basically if an atom or an element is going to get attracted to a magnet or not. Now, dimagnetism are atoms or elements that have all their orbitals, especially the ones, the degenerate orbitals, fully filled. So if you have like, let's go with our 2p, 2px, 2py, 2pz, right? If you have all of your degenerate orbitals filled up like this, you don't get attracted to a magnet. The reason why you don't get attracted to a magnet is that when you bring the atom close to a magnet, these electrons should spin to align with the magnetic field so that it gets attracted to it. Now, imagine this electron here spins to align and will cause this to repel, to spin the opposite direction, and will therefore cancel the spin charges or the spin momentum of each other. So it won't get attracted. So dimagnetisms do not get attracted to a magnet because they are fully filled. They don't have the room to spin around to align or orient their axis to the magnetic field to get attracted to them. Now, paramagnetism, on the other hand, is a whole different ballgame. It goes like the same thing, 2px, 2py, and then 2pz. follow same thing. If it is partially filled, then it will get attracted by a magnetism. So the mnemonic that I want you to pay attention here is that for a paramagnetism, the atom arranges its electrons to be parallel. Paramagnetism, parallel to the magnetic field. Once it becomes parallel to the magnetic field, it gets attracted to it. Did I make sense? So that is about paramagnetism and diamagnetism. And so if you are told to, if you give on a MCAT somewhere, you are given a group of elements and you are asked which one of these should be paramagnetic or diamagnetism, go into the electronic configuration, figure out which one has parallel or half-filled degenerate orbitals, and which one has fully filled degenerate orbitals, and see which one will get attracted to a magnet. And finally, last but not the least, to get this whole thing done with valence electron. We all know, most of us have heard what a valence electron is. Valence electron is the outermost electron that revolves around an atom. And this electron kind of or almost always dictates the behavior of the atom. The reason why it does that because it is the only electron that is involved in bonding, that is involved in chemical reactions, that can either be lost or it could be gained. Because since it is very far away from the nucleus, this is, by the way, the classical representation of an atom. Then let me draw one last one and put an electron here. I don't know which element I drew, I haven't counted the electrons. But the valence electrons, this dude here, right, is the valence electron. The valence electron, because it's the one that is the outermost. See how the distance, he is very unfortunate to be here. He does not want to be here. All his other dudes are enjoying life. He's not. He is worked against by almost 2 to 3 forces, right? That does not want him to be here. The first force is the electrostatic forces of attraction between that electron and the nucleus. See the distance? Very wide. So the forces on this holding it in place is weak. So if anything comes closer, that the electrostatic force of attraction is greater than this, it will break free and go join, thereby creating bonds. Right? Say another one that is working against it is its effective nuclear charge. The effective nuclear charge is how much force or how much energy does this nucleus use to hold Mr. Valence electrons here in place. The longer you go, the further away you go away from the nucleus, the more energy the nucleus has to exert to keep you in place. The nucleus, the positive charges here don't want to exert all that energy on you. You are a bad net, so you want to get rid of it. That is the second force working against it. The third force working against it is its own brothers and sisters, its own other electrons, the repulsive charges. Since they are all negative, they repel each other. And see, we got 2 dudes here. Same size as him. Repelling one dude that is not even held strongly by the gravity, electrostatic forces of attractions and then the effective nuclear charge. So it goes away. And it's going away with all these negatives that comes with it. This positive is that it gets to dictate the behavior of the atom in chemical compounds because it is the one that is going to interact with other elements. So it is the face of the atom. Technically, when it goes there, whatever it interacts, it represents the atom it is coming from. I'm from Ghana, right? I'm pushed here to America. If somebody is speaking to me, I am technically kind of representing Ghana. Whatever I do, they be like, oh, Ghanaians are like this, Ghanaians are like that. Same thing works with the valence electron. That is how it works. So I'll end my lecture here. I have class in the next 5 minutes. See you in the next video. We will start talking about periodic chemistry. Bye-bye.